Are we ready to start? Yes. Okay, so we welcome Bernd Kirchheim with a talk about uniqueness and convexity in the calculus of variation.
Yes, so this is going to talk about, thanks for the invitation, of course. Hope you enjoy my talk a little bit. I enjoy being here very much. It's joint work with a couple of people. One is Judith Campos Codero from Oxford. And then there are two Jans involved. Jan Collage, which somehow is on the project for many years, but somehow disappeared in Prague, and Jan Christensen. And me. So we wanted to look at some notion of convexity notion, which comes up quite natural, and maybe those of you who know a bit about the several dimensional calculus of variations, they know that unfortunately there are already a few convexity topics out there. So, and I know Vladimir Schwerak for many years when I was a student. I never was able to, I know that he did something with some of these notions, but before I started working on it, I never really understand why people need so many of these notions. And so of course, what is the topic in general? You have some f function. We live in the autonomous case, function which defines kind of a local energy for every matrix, which represent the deformation, and maybe you can also plus infinity there. It's not really the issue here. And you want to look at an energy in the most easy way. I write here omega, but you can always replace it by the unit cube. It doesn't really matter. Bounded set in Rn. And you integrate f of the gradient of u set dz. And you want to minimize this over which class, essentially, okay, it's also not too much the issue. Let's say the f has some the usual growth conditions, and then you minimize in our case over the Lipschitz perturbation of some boundary data, not function. Okay, easily the function on all of the things. Right, so this is the prototypical question. Of course, it gets more interesting for the engineers, maybe if you go to some LP spaces. Okay, here's P. But not always. Sometimes the f can become infinite if the determinant of A is negative. All these kind of things can happen. Okay, and then, of course, people know that the minimizer, they should satisfy something under some assumptions. They satisfy the Euler-Lagrange equation, divergence df reduce set identically 0. That's the first derivative of E being 0, and then the second condition comes basically the Lagrange condition, and this says something like d squared f in grad u set is basically a positive definite matrix for almost every set. So you can write xi xij is bigger or equal 0. And this is the case if n equals 1. For a general n, you have here eta, alpha, and beta. So so alpha, beta are less or equal than n, and ij are less or equal and small n. And then Hadamard does the game. I think this was basically what people did in the 18th, 19th century already. They knew this kind of conditions are there. In the beginning, they mostly looked at this equation, and the variation point of view was a bit later only involved because it didn't have the spaces which gave you the existence of the uniquenesses. There was this big argument between Weierstrass and Riemann, I think, if the Dirichlet problem approach is correct or not, because Riemann did something without proving the minimizer exists, but found interesting things anyhow. Okay, so the next person which comes on the scene is Moray. This was the only other occasion I've been in Princeton, I think 20 years ago, John, something like this. It was in 2002, there was a conference on 50 years of Moray's paper on the big convexity notion he introduced. And I was suffering.
Charles Moray?
What?
Charles Moray?
Charles Moray. I was suffering a lot.
He taught me calculus. In Berkeley.
He taught you calculus?
Yeah.
Okay. I was first year in Oxford and I had to do all the tudes and the marking, and in the middle I had to squeeze in 3 days in Prince. But okay, you do it. It was a bit younger also. Okay, and he basically looked at the questions, what kind of things can we require of the F to have the existence of minimizers? Okay. And he played it back. Existence of minimizers is one thing, but I mean, let's go to the functional analysis point of view. We want to have weak laws in the continuity of this E, right? And that's basically what he observed. I don't talk about the growth conditions. He basically said that E is weakly lower semi-continuous if and only F satisfies this inequality for every A matrix. The integral, okay, doesn't again depend on the omega, and I take the F of A plus gradient of U is bigger or equal than F of A. And this is true for every P U, which keeps the boundary datum. So I don't know. W 1 infinity 0 of omega, or you can take smoother test functions as well. Okay. And this one, the necessity is quite easy to see. I mean, if you have something which improves, a bubble which improves over a linear map, then you raise the frequencies and the bubble will converge to the linear function. Right? I mean, this picture is proving one direction. If this thing is cheaper than the connection down there, then you start making many such bubbles and you convert weakly to the flat thing. So you will disprove the lower semi-continuity. Then it implies this direction is a bit more work. You can prove it easily for linear things because you can interpolate through. If the function is not precisely having the right boundary datum, the linear boundary datum, as it approaches the function, V convergence means uniform Lipschitz constant and pointwise convergence. So uniform convergence. So then you can find smaller and smaller strips on the boundary where you can interpolate from the actual affine boundary datum to the boundary datum of the functions which you have, and you get what you need. Okay, so he observed this strange inequality, which is the Jensen inequality, but for gradients only. You don't require all functions. I mean, this conditions means the integral of the gradient itself is, of course, 0 in the space of matrices. Right? So it's just Jensen's inequality for very special gradients. It's a nice condition which nobody really understands too well, but then people say, okay, let's look how is the proof of the Legendre-Hadamard condition. Basically, you test with something eta times exponential, let's say I x times psi, and you raise the frequency k. You use such test functions for the minimizers. And you can also play around with such test functions, and then you say, okay, maybe it's easier not to use the exponential, but just look at functions which make a zigzag, perturbing the zero function with zigzag functions. And if you make the frequency higher, then it converges really weakly to the zero. Okay, and you find two gradients. One is a plus, one is a minus, and basically you get as a necessary conditions from this, you obtain that for every A and for every matrices AB, vectors AB, you find out, I put it in the simple way, f of A is less or equal than 1/2 of f of A plus A tensor B plus f of A minus A tensor B. Those are the two maps which you produce, you test them, and that's it. So of course now you know mid convexity is the same as convexity. It's the same as saying that for every A and for any vectors, every matrix of direction 1, this is a convex function. And this thing is then called rank 1 convex. And Morey did a great job writing the paper, but he was a bit lazy when it came to baptizing the child. He called it quasi-convexity. I don't know if already back then, but there's another quasi-convexity out there, which somehow means you have a function and all sublevel sets are convex, which is weaker than usual convexity. And if you check, there are many more papers written about this. And you always have to say in the sense of Morey, if you don't talk to people from calculus variations. Okay. But then, I mean, looking on this condition, actually, Alexander Habermas, it tells you in Legendre tells you for n equals 1, actually, well, you are in a convexity point of the F with your value almost everywhere. Couldn't you prove also something more here? Couldn't you prove convexity actually of the F once it's quasi-convex? And this is not true because of course a famous example. So quasi-convex does not imply F is convex. And the famous example is F of X is the determinant of X, right? It's a Lagrangian, so you can do it in many ways. It's a differential form, a closed differential form, whatever you want to say. Basically, you see that the integral of F grad U Z equals to the integral of F grad V Z if U equals V on the omega. So, and you basically can also characterize for which kind of functions of F you have this property. And these are the so-called non-Lagrangians. I will write them down in a moment, what's precisely. And then there comes, of course, the idea that you say, well, such kind of inequality and all this behavior I will also get if I have an energy F, where at every point I can touch it from below with such a null Lagrangian. It's a function which has this property. So this is F is a null Lagrangian. I think the F in general is a Lagrangian, and if it does nothing, then it's a null Lagrangian. So, and this idea, I mean, it needs some formalization, of course. With the X is you associate the minors of X, This is the xi entries, then the second minors. Third minors, and so on. Until you reach the maximum, this is in some RD. And if you want the D, what's the D? It's the sum of n over k times n over k. You sum the k, and you get all possible minors. And basically the idea comes, I talk about functions where you can touch the f in every point with a null Lagrangian. So such f has this property star if and only if there exists an L from this RD to R, which is fine. And f of x is L of the minor vector of x. This is a null Lagrangian because a linear combination of determinant of all orders. And you can also say f is quasi-convex if in case. Like you say it differently. You say f is polyconvex if there exists, instead of the L, exists a phi. And the phi is a little bit worse or more general than a phi. The phi is convex, such that f is now phi of the finals. And if you don't like the notion, you could complain to the person inventing it, so which is John. And he basically noticed that for many engineering applications, the convexity simply is too strong a condition. There are many problems when you have energies which vanish at different parts of the space of matrices. Is there a kind of energy is not convex, but is there a convexity notion which is good enough for me, for instance?
Could you give an example of what you're thinking? I don't know anything about your work, and I have no idea what kind of calculus variations problems you're really thinking about. So maybe just.
Well, for instance, what if you try to minimize such an function? I mean, if you take the square away, right, then there will be too many solutions, because this null Lagrangian tells you have basically any function is a solution for its own boundary datum. Now, if you start putting the square here, things get much more rigid. If you add the Dirichlet energy, we don't know precisely what is happening. The situation gets much worse. The underlying differential inclusions cannot be controlled. I mean, Laszlo had a beautiful proof using some algebraic geometry from his brother, algebraic geometer, and then he learned it works only in the complex world. So simply, the thing is quite funny. So such kind of problems are already good enough. Like John was basically interested, I think you were interested in h of the determinant of x, where the h becomes infinite if the determinant goes to 0 from above, and then plus norm of x squared. This would be a fully convex f. And when I first came to this question, it was more or less related that you wanted to minimize come on, as a kind of distance of the gradient of u to a set, let it write like this, SO3 times diagonal matrices M1, a set containing M1, M2, M3. When the matrices are basically is lambda squared 1 over lambda, 1 over lambda, and then you flip the things around. 1 over lambda, lambda squared, 1 over lambda. And there is a theory of this material which under a certain temperature it changes its cubic crystal cell into a kind of box. I don't know what's the English word, quarter, into a kind of something which is not a cube anymore. And the question is, how can you fit gradients which describe such a thing together? Because these cubes, I mean, it's difficult. Of course, it's easy to produce one cube only. But if you want to start mixing these cubes, it's not so clear. If you think about it, this set here is a set in matrix space. We imagine it as consisting of 3 copies of SO3. And
Lambda is fixed.
What?
Lambda is fixed.
Lambda is fixed. Lambda is close to 1, but different from 1. That's what the material does, right? You have a cube. And now this can stretch out in one direction. It can stretch out in this direction. And it can stretch out in the third direction. Basically, volume preserving is the thing one dreams of. It's not necessary always. Okay, and now the material basically above a certain temperature, this unit cell is this cubic one. So it's very hard to change anything. If you go below this temperature, then all these 3 wells, these 3 config variants are energetically equivalent. So if you now take the material and you start pulling it in this direction, it produces more and more of this kind of rectangular shapes and boxes in this direction. But it's not so easy. I mean, if you pull it completely, it's fine. But if you put some boundary datum in the middle, it has to start mixing these gradients all together. And it's not so easy. I mean, you can maybe, some of them you can mix, but this with this one you cannot combine. They are not compatible. They differ on a set which is larger which they agree on a set which is smaller than a plane of dimension 2. So basically you put a square here to have it nicer. And you try to minimize.
Where does the temperature come in here?
What?
Where does the temperature come in here?
The temperature is once and forever chosen. So it's, if you're in a high temperature regime,
Are you looking at, you're not doing statistical mechanics, you're just doing variation?
No, we just noticed that
So temperature means, are you varying lambda or? I'm not quite sure.
well, basically the lambda depends. So if you are, let's say, the temperature is above some T0, then lambda equals 1. Okay. And then if the temperature goes below 0, the lambda starts getting presumably larger than 1 slowly.
But lambda depends on the temperature.
Lambda depends on
That's
the
all.
question.
But there is no energy, there's no energy balance how the temperature works and so on. It's simply material which is quite soft at room temperature, and you can change the shape, and then you heat it up and it jumps back to the original shape.
That's modeled by changing lambda.
Yeah, it's a solid, it's a crystalline phase transition. And he's just kind of stating the energy in the regime below the.
That's why we got into this, and you see now this distance function is vanishing here, here, and here, so it will never be a convex one. Yeah. But it will be basically because there's a rank 1 connection, there's the matrix here and here, they differ only by rank 1. So the energy should be also, if I want to find a minimizer, I have to replace this by something which is which is the largest quasi-convex function, below it, and this will be zero also on this set, but it will not be zero everywhere. So these are the right convexity notions which come up here, because you start from something which is not convex. Okay, and then, as I said, these were the notions which are around. So the polyconvexity is really, sorry to say, it's man-made, it's made by somebody for applications really at hand. And the other two notion, one convexity is just the Legendre-Hadamard condition, which you hardly avoid. And then there is the condition by Morey, which is come precisely to the point, but nobody really understands it too well. So one of the highlights of the results is that there exist functions if n is bigger equals, or n equals 3, and n equals 2 is the minimum, then there exists an f which is rank 1 convex, but not quasi-convex. So this is by Vladimir Schwerak in 1950. So what is the situation for this in 2 times 2 dimensions is not clear at all. If you could prove it, it would have a profound impact, of course, on complex analysis, because many integral inequalities, you write it down for some integrand, for the integrand to check out if it's convex in all rank 1 directions is in 2 times 2 is not so difficult. And it would give you some, and then you say, okay, but then you should easily be able to find counterexamples, but even this is not clear. So, and here there are some progresses, minor progresses made, but we're far away from closing this final thing up. Okay, and now there comes another question in the game, because very often people say, we do not just want the existence of minimizers which we get by the direct methods, we want also uniqueness of minimizers. What happens if I know that you have a unique minimizer? And not just a unique minimizer, for the original problem, you allow only also some perturbation. So let's look like this. The question is, you have E of H of U is normal energy E of U, integral F grad U, plus some linear functional of U itself. It's not of the derivatives general. So you can imagine this is, for instance, something like integral of U against some H integrated. So H would be external force which pulls the thing down or something like this. So it's a low order term. And we ask the question, what can we say about the F if we have unique minimizers for such Y star which are acting somehow on the space where the U is from? People looked at this. I think Rockefeller had some work. If you have a functional and some linear perturbation and you always have minimizers, what can you say about the functional?
But you have a minimizer for any, I mean, you have a unique minimizer for any linear perturbation.
This is what they looked at, Rockefeller. And of course, all this story is long with the, I mean, there was even the notion of a semi-reflexive space, which was a space so that almost a dense set of linear functions that took a maximum on the sphere. Later they found out actually every space is semi-reflexive, so they dropped this notion. And then they looked at the spaces where every function has a minimum. And then there's a James theory which tells you this means reflexivity. So for the linear ones, the thing is very clear. And if you have it for everyone, for every linear perturbation, then the E is expected to be convex on the space where you are working, on the Sobolev space. And in 2013, there was an interesting observation by Saint-Raymond. And he basically said, if you put it more general, so you have this E from X is now a reflexive space, otherwise it will not work anyhow, into R, or this extension, doesn't matter so much, such that there exists a set D, and for every Y star in D, you can look at the minimizers of E minus Y star. And this is convex and non-empty. What is the assumption about D? D is convex and norm dense. So, and then he concludes that E is basically convex on X. What's the point about this relaxation for D? Because if you're in the usual case of a Sobolev space, you wouldn't like somebody coming and disturbing your energy with some integral. So this Y star, somewhere down. It's basically this integral U times H, and this H would be a horribly bad function, which is in the fifth class of Baer, or, you know, is everywhere discontinuous. But in this setting, you can basically use smooth functions, right? You can smooth forces use. You can say it's unique under perturbation with smooth forces, because the smooth functions here are basically dense in all the spaces you have. That's why this result got very interesting. It's a revision of the old stuff by Rockefeller, but has a new proof. And there are all kinds of results around this, but I will not talk much on it, what can be done. There's another proof by some convexity group. He uses James' theorem. The convexity people calculate really the second Legendre transform of E and prove its E star star is E, so it must be a convex function. And we also worked a little bit on this proof, and maybe more accessible for the analysis people. But we are left, if you do calculus variations, you are left in the situation, what can you say about such an E, which now has this property? And to first get the definition right, we call E functionally convex if it has is functionally convex if, okay, now you can say whatever you want for every omega and for every G, which is, let's put it like this, it doesn't really matter. Omega E, corresponding E, is on G plus W1 infinity. 0 omega is convex. And this is the case if and only if there exists one such omega 0 and one such G0. But the same conclusion holds true. It's independent of the boundary datum, it's independent of the domain. And the picture is the usual proof. You have one example, okay, and you have another domain and another G. Do you take this example and you rescale it properly, right? And then you place a copy of the thing here, and you interpolate your boundary datum to the boundary datum here. And now you see, if you change this function here, you can directly recalculate in what you have here. And if this function here is convex over this space, the large function will be convex here. So different G and different domain is no big issue.
Sorry, Bernd, I'm getting confused about something rather basic. So initially, when you start out with Maury's notion of quasi-convexity, it's the condition that's necessarily insufficient for weak lower semi-continuity of the function V. Now it seems you're asking for something stronger, which is that this functional E should be convex, not weakly sober. So is that the game? Somehow you want to use general functional analysis properties of convexity to kind of...
Well, we expect, I mean, we will of course show that it's more than Maury, basically. But it's something which would tell you that you have non-uniqueness of minimizers for certain perturbations. I mean, this question, if strictly polyconvex functions in this sense have unique minimizers, was a question Emanuele Spadaro was working on it, so student of Camillo, and before there was work by Brian White and Lars Offerman. So John asked this question, and I think Emanuele proved that for polyconvex functions, you don't have uniqueness for a specific one. I mean, we get it more like for certain perturbations, you don't have uniqueness of minimizers. Okay. So this is the notion, and I said it's independent of the boundary datum of omega 0. Of course, we have to fix a boundary datum. If you allow the whole space, then you simply take a fine function and you change it, and then you get convexity. Nothing interesting comes up. You can wonder if you have to fix a boundary datum on part of the boundary if it changes much. I don't know. But what can we say about it? And there's one observation. Let's say we have such an F, and we perturb still around a linear function. So we take E of t is energy, I'll write it like this, F of A plus gradient t times gradient of u in z, dz. The u is, of course, let's say compactly supported, whatever, boundary 0. Omega. So we preserve the boundary datum. So this has to be a convex function in T, right? Because if I convex. Now the F, okay, in principle, we will know they are smooth enough. So if you calculate the derivative of this in the point 0, then you basically get its df in the place A times grad u z dz, and this is of course 0 because this is a constant and the A has this average property 0. So this is 0. So it follows immediately that E is increasing by convexity on 0, 1. In particular, E of 1 is bigger or equal than E0, so it's quasi-convex. So, and then if you know this, basically you justify that the F can be supposed to be smooth enough and whatever. It's not a bad function. A quasi-convex function is a rank 1 convex function. A function is already convex on so many lines which generate the whole space. It's a Lipschitz function locally, so you get a lot of nice results. And by some new result of Jonas Hirsch, basically that's being printed. Basically, it says that such F, such, and all rank 1 convex F have almost everywhere a second derivative. So he generalizes the Alexandrov statement for this function. Which is good because in some sense, if you want to verify all these kind of conditions you are after, also for you want to make the Lagrange equation explicit, it's good to have function differential. But this property is maybe even more interesting for me, that E is increasing, and this was called the F prime. Basically, it means that you can integrate, so E increasing means that the integral of d f a squared u is non-negative, and this is something people called f is quasi-monotone. If the derivative is quasi-monotone. So we all know that convex function has a monotone gradient. This is the same property, right? If you perturb and you multiply with the thing, then on average you get something. If you don't want to use the derivative, you want to use this condition only, then you will say this one we will call E has a quasi-monotone slope. It's a unique formulation. In fact, in case if the f is not as nice as we want, something is wrong. This is a necessary condition on top of monotone function of quasi-convexity, and then you can look which functions do satisfy it. It is an old result by Hamburger, which nobody ever seen written down, but it's known that he had this result. And he comes back to this case. He says determinant of x squared is not, it doesn't have a quasi-monotone slope. Right, so already the first examples, it's, well, you take a nice function, which is given a functionally convex integrand, and you start do something convex with it, you square it, and it gets worse. The idea is not so difficult. I mean, you have a theory how we can cook up strange functions, and the notation is very brief. So basically, if we identify a point AB with a matrix A, B, 0, 0, okay, and now we look at functions, what kind of gradients can they have? And I claim you find basically if I give you three matrices, this one, and this one, so this is configuration like this. Be precise, this one is the point -1, -1. This is the point 1, -1, and this is the point 1. This is 0, 1. Okay, then I claim I can find a function whose gradient is basically living on these 3 points. In general, the theory tells you if the points are one connected, you can combine the gradients and then you get this result. I mean, the picture is fairly easy. First, you split it up and you divide the thing, I don't know, 6 strips, let's make it. Here. Next, so I draw you U2. U will go from R2 into R2. And the U2 will basically look like, in the first step, I don't change the first coordinate of the function is 0 still, and the second one makes this wiggle. Which means that you already produce a gradient 1, 0. 1, you produce the gradient 0, 1. If it grows up and you produce the gradient 0, minus 1, if it goes down. So I say here it's 0, 1. So this is a good gradient, this is a good gradient, this is a good gradient we are using. And on this one, so you have the wrong gradients, but now you can start wiggling the function in this direction. So the U1 will now become perturbed like this. Of course, the things do not fit together in the boundary, not at all. But if you make the perturbation very small and high frequency, then you get very narrow strips where you have to interpolate through. And after all, if you look in the integrand efficiently, the function is only using, the distribution of this function is only using this gradients. This one with 1/4, this one with 1/4, and this one with 1/2. Okay, and now the guy said, go in the situation again, go here to the point 1, 0, take a function whose gradients are roughly like what I've done, live on these 2 points, and then you start. This is my matrix A0, is 0, 1, this point. And then you add to A0, you add t times this metric function which I constructed. And you see basically the gradients will be moving on this. Right? I mean, originally the function is just the gradient, it's just A0, now the gradient starts splitting out. And the determinant square is lurking here. It's positive here, it's positive here. It's 0 here, it's 0 here, it's 0 here. So E of 0 equals E of 1, because then you are already down here on the determinant 0. And E of 1/2 is positive. Because you have the gradient here where the problem is. And of course, you see, if you would use the determinant, this and this will always compensate. But if you take the square of the determinant, you kill this condition of functional convexity. And therefore, you know that certain perturbations of this will have non-unique minimizers, even if you, in some sense, have a quite nice convex object. So this is the old idea by Hamburger. We basically, very rich space. So you can basically, along these lines, then find a proposition which says, I define what are these minors, and it says this problem always comes up if you use a strictly convex function or a non-two-flat function for the minors. So it's like this: if f of x is of the kind phi, and here I don't take all the minors, but I call it minus p, the proper ones, order bigger or equal than 2, so not like ones, of x. And of course, a phi is convex. Then if f is functionally convex, it follows that phi is affine, linear. So it's not just the determinant in 2 dimensions, it's always the case. Whenever you use strict convexity on the minors, it creates problems like this. Of course, you can compensate these problems if you have enough convexity in the entries itself, right? It's not true that you cannot do it. But a third order can never be compensated by a second order.
So if I add a large gradient of u squared, then of course I will be able to compensate.
Of course, you do something. I mean, I don't know precisely. You couldn't add the norm just because if you go far out and the determinant is order 3, it kills it. But you can at something sufficiently convex.
Mhm.
To get a hands on this. So it's quite hard to find such functions. And then there's another basically result. I also not prove it, but this is basically the main work we have. And it says if the F is functionally convex and this growth condition I mentioned one in the beginning, F of A is less or equal than C times 1 plus A to the P. For P is less than 2. So just good enough to get rid of the determinant. Then it follows that F is convex itself. No fully convexity, nothing is really convex, the situation. And it uses the fact we look at the derivative of F, and the derivative of F is then a function which has a sublinear growth. And essentially,
sorry, but with that growth condition, haven't you got rid of any proper minor whatsoever?
yes, there's nothing there.
Okay, yeah.
There's nothing there. Now the question comes, of course, what happens if P
I mean,
equals...
because you said the determinant, but you really got rid of actually anything.
Yeah, but I'm in 2 dimensions.
Yeah, okay.
Yes. So the question is what happens if you are between 2 and 3, right? For instance. And so we have some special results in this case, but they are not at all satisfying. So there's one result saying if F goes from R2 times 2 into R, and it's isotropic. It means it depends only on the eigenvalues, basically. I mean, it's invariant under SO2. And so what else is the condition? Yes, the growth condition, I will put it slightly different.
But why would 3 be relevant at this point? I mean, you're allowing the determinant, so I wouldn't imagine that makes a big difference, 3 or infinity.
Okay. So the real condition we put actually on the second derivative of F, this should be sublinear. Then F equals C times determinant plus convex function, plus a convex function. So something like this you hope always, right? I mean, for the quadratic ones, if you're quadratic form, then this is also result by Marcellini. If you are basically functional convexity on quadratic forms is the same as rank 1 convexity, because then you're positive and you're positive works. If you go above this, it's not so easy. And what you really do, you cannot look at quasi-monotonicity only anymore. You replace the A by something more general. Okay? So, and then you get basically the condition that this E prime is positive corresponds to the fact that D squared F and you have basically any function around which you perturb around, and then you take the grad U. This should be non-negative. Well, now comes the nice argument. If the D square is sublinearly growing, you can use Alberti's theorem, because you can basically say, on this level, I can approximate any gradient by any function, basically. You don't feel it on this point. I mean, the remainder, which is somewhere around, it stays integrable and it disappears if you push it to infinity. And so here you can put a general function instead of a gradient. And then you start playing some games. But if you are bigger than 3, so if you are 3 and you know that the function is if you're below 3 and you know that the function is rank 1 convex, then the second gradient has a good chance to not to grow too fast. Yeah? But if you go higher, then you have no information anymore left, and it's not clear at all. But we are more optimistic. We would hope a result like this being true if I replace isotropic by 2 homogeneous. And of course, all the time f is functionally convex. If you replace isotropic by 2 homogeneous, so it's the case p equals 2, just not for the determinant, for the general, not for the quadratic form, then we would still believe we should end up here. Because in Marcellinus result, you end up with a positive quadratic form. So this is the thing we really basically most annoying problem because it's the simplest one. Yeah. And then a few other remarks which you can do with this kind of things. So from the functional analytic side, it's quite clean, the picture now. There are 2 proofs of this result about the convexity, and the implications which it really has for integrands are, we think about them and try to understand. I think that's what I wanted to tell you.
Questions?
So at the end of the day, what interesting examples do you have? I mean, there's the quadratic case that you mentioned in Helsing, the Jean-de-Hadamard case, that gives you a functional convex.
Which,
Right, which is not a non-convex integrand, which gives the integral convex. Right? But apart from that, what other interesting examples do you have?
well, you take a non-convex set in the conformal matrices, you take the distance function squared, which is something like Bob Cohn. I mean, this distance to 2 points. So the classical distance to the 2 points. And what is Bob Cohn doing? And then you take the square. You take the square of the distance and you take the quasi-convexification of this. So here's a formula for this. For his 2 points, you can calculate it, but in general, you can also prove this is the relaxation of this energy should have unique minimizers. If the thing is in the conformal matrices, because then the quasi-convexification isn't increasing the 0 set. It lowers the function outside a little bit, but because we have conformal matrices, there is never a rank 1 connection, so the quasi-convexification of the distance function doesn't pull it down. It makes it smoother a little bit, but this gives you something which is not of the determinant type, it's not convex. And okay, and then coming back, I forgot, coming back to the Hamburger example. It was studied, of course, then in more detail. So x to the 4th plus k times determinant x squared.
That's what I was about to actually ask you.
That's what people investigated. I think Kawei.
So now I see the difference between 3 and 4, for instance. So can this be functionally convex?
Yes. Okay. I think
a sufficiently small k. I guess.
Yes. Shang and Hrabowski, what was the name of the guy? You want to know him? Kawei Shang. They proved this is quasi-monotone if and only if k is between -2 and 8. And then there was very recent work by Bijang Yang and his, presumably a new guy, Kim, and they proved it is functionally convex if and only if it's convex if and only if you are, I think, between -2 and 2. So this is the case when the determinant can't mess around with the.
But then it's really convex.
It's really convex. So they don't have a new technology how to prove functional convexity. This theorem, there is something going on in this theorem. I mean, I didn't have time to show the proof.
So you don't have an example which is functionally convex, but not
It comes here,
linear.
between 2 and 8.
Between 2 and 8.
You're not functionally convex, but you're creating mono.
Yeah, no, but I mean, you don't have an example which is functionally convex and not like, a linear guy, a polyaffine plus convex. I mean, at least not that you mentioned.
Not that I mentioned, no.
Because, yeah, okay.
Okay, so I
mean, the
so
affine-
this example I mentioned to John, so you take the distance function in R2 times 2, you take the distance function to some, maybe only to 2 point sets, you square it, and then you take the created convex envelope of it.
The quadratic case is not polyaffine in general, right? Even though it's functionally convex, right?
The determinant squared.
No, the general quadratic thing. So
Yeah.
That's not polyaffine. That's the counterexample. Or the terrestrials.
Okay, yeah.
But it is functionally convex. If it satisfies the different Hadamard condition.
Yeah, but it's, yes. But you had our convex term on top of it, or what was it?
Yes. Yeah.
Well, don't know if I can exclude something like this, yeah. Convex term, only, I mean, the quadratic case for 2 times 2, it's determinant plus something quadratic, quadratic form, positive.
Yeah. So it is still polyaffine plus convex, no? Or am I missing something?
Well, as soon as you go above 2, yeah, you could hope that
Mhm.
you have something there. But of course, I mean, if you spend too much convexity here, right, you might have problems.
At infinity.
I mean, it's not just locally. Locally, you can do many things somehow.
Mhm.
So you could use, presumably, you could try to use the determinant to get the negative part somehow. Like the gradient and then to fix it somewhere else. I don't know. Okay, so above 3, basically, nothing is clear. We have no idea because the Giovanni theorem doesn't allow to make any reduction.
Do we have other questions? Let's next figure again.